thank you. I'm Mark Tucker. So I've been at SideFX for about 20 years. The last 5 or 6 of those, I've been the lead developer on the Solaris project. And so I'm here to tell you more than you ever wanted to know about how Solaris works, with the goal of allowing you to make better LOP networks. So who is this talk for? I'm going to talk a little bit about C++ classes and a bit about writing LOP nodes in C++. So if you're a developer working on C++ LOP nodes, this is for you. If you're a TD who wants to optimize their tools and workflows, so you're writing Python LOPs, you're putting together templates and LOP networks for people, there's going to be a lot of stuff for you too. And for anyone who just wants to know what the hell's going on. I'm just going to assume that you know USD stuff, that you know Houdini stuff, that you know LOP stuff. The C++ stuff, I'll be giving some class names, but you can just ignore it and you won't miss much. And most of what I'm going to be saying, I've put into the slides. And so I could have just handed out the slides. So the value of me actually being here and saying this stuff out loud is so that you can stick up your hands and say, what are you talking about? That doesn't make any sense. Why? Tell me more. So as I'm going through, please interrupt me. I think that will make it more useful for everybody. So I'm going to start at the beginning. When you have a LOP network, it makes a USD stage. What does that USD stage look like? Well, every USD stage has a root layer and a session layer. So in LOPs, the root layer is always completely empty, except for root prim metadata that has to be on the root layer, according to the rules of USD, and then a list of sublayers. The strongest sublayer is always the current LOP's active layer. So that's the layer that is edited by the current LOP node. And then there can be more LOP layers, more SOP layers, more USD layers from disk, any number of extra layers. And the contents of all those layers is completely irrelevant. It can be anything at all. And then you've got your session layer. So when you're working in a LOP network, your session layer is empty, and it should stay empty. The session layers are only used by the viewport. They should be set by the scene graph tree and other custom UI widgets only. And the reason for that is that they're actually owned by the LOP network, not by any particular LOP node. So when you move from LOP node to LOP node, there's nowhere to store this information. We're not tracking it. But we do have, so we have a sort of set of well-defined sublayers of the session layer for storing specific pieces of information. One of them is like this custom layer. And so if you want to write a custom UI that only affects the viewport, then you can make use of that custom session layer. But if you're writing LOP nodes, don't touch them. So LOP nodes all create a USD stage. So you can go to any LOP node and say, hey, what's your USD stage? But each LOP node does not own a USD stage, because that would make LOPs ridiculously slow and use up tons and tons of memory. So every LOP can generate a USD stage. So each LOP node owns this C++ object, an HUSD data handle, which is really a shared pointer to this real object that contains the useful information, which is the XUSD data object. And the XUSD data object has a shared pointer to a USD stage. Now, if you have a bunch of LOP nodes in a chain, every one of them has their own data handle, everyone has their own XUSD data, but a bunch of XUSD datas in a chain can all point to the same USD stage. And that's that right there is like how LOPs can work. So the XUSD data contains enough information to make that USD stage from scratch, or to take the USD stage in whatever form, whatever state it's in right now, and morph it into the state that is equal to the output of a given LOP node. The XUSD data also contains other stuff like the stage context, so stuff like layer muting and population masks and that kind of thing. So just to prove to you, if you want to go home and see that, oh yes, we really do share stages, You just have a cube lop and a sphere lop, and you ask the cube lop for its stage, and you say, hey, cube lop stage, tell me about sphere 1, and of course it says there's no such thing as sphere 1. And then you go to the sphere lop, and you say, hey, sphere lop, give me your stage, and then you go back to the cube stage, and you say, give me sphere 1, and it says, sure, here it is, which obviously makes no sense unless you realize that sphere 1 and cube 1, those lop nodes are using the same stage. So in order to get at a USD stage from a lop node, you have to do what's called locking the stage. And so you go to a lop node and you get its data handle and you say lock the stage, which is basically saying give me the stage for this lop node. And that tells the XUSD data to lock, which takes the shared stage, morphs it into the right form, and then you get back the USD stage. If you then go to another lop node that's sharing the same stage, and you say, hey, I also want your USD stage, it'll say the data handle will go to the XUSD data and say, give me the stage, and it'll go and it'll try to morph the stage, and it'll say, oh wait, somebody's already locked it, I can't do that. And so what it will do is the XUSD data, as I said earlier, contains everything it needs to create the stage from scratch. So that's what it's going to do. It's going to create a brand new stage, and it's going to be, so you're not sharing that stage anymore. And you've wasted a ton of time recomposing the whole stage, a ton of memory, making a second copy of the stage. So a large part of making sure that your lop nodes and your lop networks work quickly is don't ever do this. If you ever see a warning on your Python lop that says read lock failed because of existing lock, that's what's happened. It's made a new copy of the stage because you asked for it when you already held the lock to it. So don't do that. So there are 3 types of stage locks. You can get a read lock, a write lock, or a layer lock. Read lock is for reading from the stage. So this is what happens when you do the lopnode.stage method. It gives you read access to the composed stage. It gives you read access to the active layer. I say read access. Really what we do there is we tell the USD library that all those sublayers on the stage, we say, these are read-only. You do not have permission to edit. And so that if you try to do anything, the USD library will say, no, we can't do that. But we do nothing to stop you from saying, give me permission to edit this layer. So you can always get around all these things, but don't. If you do, it might seem like it's going to work. It might seem like it does work, but then something will happen, and if the XUSD data object doesn't know about it, we can't morph back. So like you'll get very confused. So don't break the rules just because you can. So read locks don't need to be exclusive. If you can relock the same lop node several times. Generally, it doesn't happen. Generally, there's no reason to do that. So that's just kind of a point of interest. And so read locks, you create them for when you're cooking a lop node, when you're evaluating expressions that refer to a lop node stage, when you're displaying the UI, the viewport has to take a read lock. Anytime you need a USD stage, scene graph tree, when you're evaluating primitive patterns, this is one that sometimes people don't think about. To evaluate a primitive pattern on a stage, you still need the stage. So that's gonna get a read lock of the stage as well, which is why the who.lop selection rule functions to evaluate and return a list of primitives. You have to pass in a node because it's going to take that node and it's going to get that node's stage by locking it. With the lopnode.stage method in Python, we get the read lock, we get the USD stage, and then we immediately release the read lock, which is why you can write weird code like I had with the cube lop and the sphere lop. Because you still have that stage, that USD stage object in Python, but that stage might be getting changed under the hood on you. So again, don't do that. If you ever need, our Python code is run serially. So if you call stage, you don't need to worry about anybody else morphing the stage as long as you're still in that function, as long as you're still handling that method. And so you can keep using that same stage object. But as soon as you leave that function, maybe you should think about next time you do stage, call lopnode.stage again. If that lop node was the last one to return its stage, then the morphine doesn't need to actually do anything, so it should be nice and quick. Not quite as quick as using the USD stage directly, but not too bad. So that's read locks. Write locks and layer locks should only be used within the cook method of a lop node. And so a write lock is equivalent, is what happens when you call lop node.editable stage. I feel like I'm talking really fast, and I'm just like roaring through this stuff, and nobody's putting up their hands. So I'm going to assume that means I'm doing an awesome job. Yes? Is there going to be a PowerPoint of this? Sure. No other questions? Okay, I'll just keep going. I may be done in 15 minutes, I don't know. Okay, so yes, when you have a write lock, it gives you editable access to the USD stage, and it has set the edit target to the active layer. And I apologize, I've drawn this layer stack upside down. The active layer should be at the top because it's the strongest sublayer. But yeah, so you have the stage, you have the edit target set for you, and you can call whatever USD APIs you want to make edits, and those edits are going to get directed to that active layer. Those edits are immediately applied to the stage. So if you set an attribute and then you go to the stage and you read the attribute off the stage, you're going to get back the value that you just wrote there, not the value that was there before. So if you need to remember the value from before, read it before you write it. When you unlock the write lock, the USD stage itself doesn't have to change at all, but we take that active layer and we make a copy of it into your XUSD data because you're going to need that later if this shared stage changes, and then you need to go back to the state of the output of that lop node. The Python lop unlocks the write lock automatically when the cook finishes. A layer lock, which is what happens when you call lop node.editable layer in a Python lop, does something quite different. Again, I've drawn the thing upside down. I apologize for that. When you get the layer lock, what happens is we take the active layer and we copy it into the XUSD data first. And then the editable layer that you get back is that copy. So it's not on the stage at all. So you can do whatever you want to that layer, and it will be instantaneously fast. You can only use SDF APIs because it's not on the stage, so you can't use the USD APIs. But if you can make your edits by only using SDF APIs, this is definitely the fastest way to do things. When you make writes to it, because it's not on the stage, you still have access to that USD stage. You have read access to it. There's no edit target set on it, or if there is, anyway, you don't have permissions to edit any of the layers on the USD stage, but you can still read from it, so you can go look at that stage and figure out what you need to do and use those to make your SDF edits. And again, when the cook finishes and the layer lock gets released, again, we don't really need to do anything at all. We don't even need to copy the active layer into the XUSD data. And the USD stage is actually left not in the state of the output of that lop node. Again, there's no reason you should care about that, just an interesting point that it doesn't actually have to do anything to the USD stage when a layer lock gets released. Python lops unlock the layer lock when the cook finishes. I apologize for that typo. And in C++, you can build a layer lock from a write lock, but you're still in this structure, and the layer lock will return your active layer on the stage. But you should pretend you're in this setup, but you also need to be careful that you don't make edits that are illegal in this sense. So you have to be careful with your SDF change blocks. Again, that only matters if you're doing C++ stuff. If you're in Python, don't worry about it. You're safe, you're off to the side. And in C++, again, you're safe and off to the side as long as you start with a layer lock. So how should a lop node cook? Evaluate all your parameters first before trying to touch the stage. Because again, this one's the worst one because most of the time it'll work just fine. But if a user writes an expression in a parameter that refers to a stage that is shared with this lop node, and you've already locked your stage, then that expression that's just trying to read the radius of a sphere, that's going to lock another lop node with the same shared stage, and it's going to make an entire duplicate of your stage just to find out the radius of that sphere. So always evaluate your parameters before you lock your stage. And then you cycle through your connected inputs, reading off whatever data you need to get out of that input. Again, only hold one of those locks at a time. Again, you might be able to hold multiple of them at once, but only if you're lucky. So if the user makes a lop network that's, feeds in here and then connects to 2 inputs of your lop node, and you try to lock them both, and you're going to end up double locking the stage. Yes?
So can you give an example at which point the stage, for instance, in the Python log would be locked? So is it a specific function call?
Yeah. Yes. In a Python lop, the stage becomes locked when you call editable stage or editable layer.
So it's like evaluate parameters and then get editable stage, and then it's like
Yep. The reference lop and the sublayer lop have that multi-input thing, and that allows you to compose the stage from another set of lop nodes onto your stage. You can't do that in Python. You have to do that with C++, and you do that with something called the locked stage registry. And what the locked stage registry does is it actually makes a copy of the input node's USD stage, and it stashes it somewhere where it's safe. Because again, if you just use the USD stage returned by that lop node's cook method and you just put that on your stage, well, that's the morphable stage, right? That's the one that's going to change all the time. And so you don't want that sitting on your stage coming out of your lop node. So don't try to look at the inputs of a Python lop and add them as a reference or a sublayer to your output stage. It's not going to work. And then once you've gathered all that information and you've done your locked stage registry stuff and you have all the stages that you're going to compose on, or all the layers that you're going to compose onto the stage, then you lock the data handle and make your edits. So what are you allowed to do in a lop cook method? So you can do whatever you want to the active layer. You can add sublayers to the root layer. They can be lop layers, they can be layers on disk, they can be layers that point to SOP nodes. If you're using C++, you can flatten the layer stack or you can flatten the whole stage. If you're using C++, you can modify root layer metadata. And if you're using C++, you can modify the stage context, so layer muting, population masks, resolver context, that kind of stuff. What's not allowed is anything other than that. So don't edit any other layers on the stage. Don't touch the session layers. And don't use Python to edit the stage context or the root layer metadata. Because if you do it in Python, the XUSD data object doesn't know that you've done it. And so we can't, again, we've lost the ability to reconstruct that stage faithfully from scratch. And so something's going to break at some point. So how do you make a lop node that runs quickly? So like I said before, use a layer lock if you can, and apply your edits using only SDF APIs. It's fine to break your cook method into multiple parts, but again, that only works in C++. I should probably make it so that you can do that in Python as well. But right now you can't. So in C++, you can get a layer lock, make a bunch of SDF edits. It's very common in our lop nodes to do that to create primitives, because creating primitives tends to be slow if you're using USD APIs and you're doing it one at a time. So use your layer lock, add all your prims, unlock the layer lock, and then get a write lock. And that works just fine. I want to say recently, but it was probably 3 years ago that we started adding the ability to some of our lop nodes to cook a whole frame range all at once. And so the edit properties lop, for example, will run through all your time steps and evaluate its parameters at every time step and put all of that data all at once in one cook onto your stage. And that's going to be a whole lot faster because you're not introducing time dependency. And anytime you can avoid creating time dependency, it's a good thing. And again, in C++ only, we have this feature called layer checkpointing, which is a neat little optimization for certain kinds of LOP nodes, certain kinds of operations you might want to do. And what this does is it basically takes the state of the active layer and it puts it off to the side and holds that in the LOP node. And then the next time you cook, if you are able to recognize, hey, nothing important has changed since last time, or maybe I know that only this one parm has changed, and so I know how to update just that one parm, you can take the checkpoint layer and you can copy it onto your active layer and then just make the very selective edits. So the stage manager does this because the stage manager, for example, does just a whole sequence of operations. So, one for each multi-parm instance. So it may want to do 150 separate things. And so after you have done 140 of those things, we say make a checkpoint. And then the next time we cook, if nothing has changed in those first 140 multi-parm instances, which it probably hasn't, then we take the checkpoint and we say, oh, start from that point, and then you only need to apply the last 10 edits. So that particular workflow is specific to the stage manager, but I'm sure there are lots of use cases that you can come up with for how you can make use of that. The smarts of the checkpoint stuff, the reason checkpointing is better than making your own cache layer, which you absolutely can also do, you can just stick it in your LOP node, hold on to a layer, is that the checkpointing automatically invalidates itself if any node upstream changes. And so you don't need to be watching all your upstream nodes and doing that invalidation yourself. Because with checkpointing, we assume, oh, if something upstream changed, we can't make any assumptions about, that the parm expressions evaluate the same way, that your prim patterns evaluate the same way. So we just throw away the checkpoint for you. So let's say you're not writing LOP nodes, you're just making LOP networks. So how do you make your LOP networks fast? So like every other node in Houdini, if you change a node upstream, that dirties all of its outputs and all of those nodes' outputs and so on. The dirtiness just propagates all the way down to any connected node. Which means that if you are changing a node up here at the top and you're displaying a node at the bottom, a change at the top means that all the nodes in between have to cook so that the viewport can update. If possible, keep often edited nodes near the bottom. If you can avoid time dependency, do it. If you have time dependency that has to be at the top for some reason, maybe you can use a cache node to stop the time dependency at some point. But the multi-sample cooking is a great way to prevent the time dependency in the first place, which is the best way to go. Again, if you make a change at the top, everything down to the bottom has to cook. So the fastest cook is the one that doesn't happen. So if you can split your long chain of nodes into a bunch of shorter chains of nodes and you feed them into the merge, that's generally equivalent to a single long chain. But it means that if you're equivalent in the sense that the final USD stage that you get at the end is probably going to be the same. But if you change something at the top, at the top of one of these short chains feeding into the merge, then only that short chain plus the merge needs to cook. Merge is pretty fast these days. It's fastest if you put it in separate layers mode instead of the default simple mode. Generally speaking, I'd say prefer Python to Vex. The exceptions there are if you are in SOPs and you're accessing USD data, then you're probably writing your SOPs in Vex. And so, you're going to want to use those Vex functions to get at the LOP data. If you are writing if you're accessing SOP data from LOPs, you might also want to go with Vex because, again, Vex is so much better at talking to SOPs than Python is. You have to decide between, Python is better for USD, Vex is better for Houdini geometry, so you have to make that decision. And then, always use the profiler. If you're not sure and or even if you think you are sure, use the profiler. And if you see something in the profiler that doesn't make sense, why is this node taking 4 minutes? Let us know, because we want to make things faster too. And I just want to point out that the lop cooks in the profiler, you can twirl them open, and you get your time broken down into a few useful sub pieces. So primitive pattern evaluation gets split out. You would be surprised how often that is a big problem. Or maybe you wouldn't be surprised. Maybe you're like, of course it's a big problem. But anyway, it can be a big problem. The composing of the USD stage is split out. The time that it takes to stash that active layer off to the side, that's split out. And so you can use that to narrow down exactly why your lop networks are slow and maybe do something about it. Primitive patterns, they can be slow. So how do you make them faster? Again, the fastest primitive pattern evaluation is one that doesn't happen. So take advantage of pruning whenever you can. Primitive patterns evaluate left to right. And so if you put as your first thing, /foo/bar, ***, then anything that's not under foo bar, immediately pruned. You never even have to look at it. The stuff to the right never has to know about it. So that's going to save you time. Use the %kind auto collection. Use auto collections whenever you can. Auto collections are way faster than the alternative, which is usually VEX expressions. VEX expressions should only be used if you have to, because they're slow not running the VEX code. They're slow translating the USD into a form that VEX can run on, and then taking the output and translating it back. But yes, avoid VEX expressions if you can. And if you are a C++ developer, and or even if you're not and you want to learn, you can write your own auto collections. They're pretty simple to write with the HDK. It's just a couple of functions. Most of it's USD kind of code. And so, yeah, if you find yourself doing something with a VEX expression and you're like, boy, this is taking a long time, maybe you can just write an auto collection yourself, or submit an RFE and ask us to do it. Maybe we'll do it. I'm going to talk a little bit about how we morph the stage from the state of one lop node to another, or from the state of one XUSD data to another. Again, I don't know why you'd need to know this, but it's kind of interesting, so I'm going to tell you. Basically, the XUSD data, the main part of it is just an array of sublayers. And then we compare that to the list of sublayers on the root layer of the stage at any given moment. And we run through those two arrays, and if the stage has something that is not on the XUSD data, then we kick it off. If the XUSD data has something that's not on the stage, then we add it to the stage. If you're dealing with lop layers, when I say add and remove sublayers, we don't actually add and remove the sublayers. Removing them, we just clear them, and adding them, we do what's called a transfer content, which is just a USD function that copies the contents of one layer into another layer. And it's a super smart function that only makes edits when things are different. The reason that all of this matters, adding and removing sublayers is bad because it tends to make USD recompose the whole stage. And even worse than that, it tends to make Hydra refresh all of your primitives. So adding and removing sublayers, we work really hard to avoid that. When you create a new empty USD stage in lops, even we just put a bunch of placeholder layers in there, like just empty layers, so that when you start adding lop data, we don't ever have to do that, add a sublayer, even on that first cook. And once you add a sublayer to a USD stage, no matter how far up the chain you go and how many lop layers we strip off, you can have 30, 50, 100 placeholder layers, and they'll just sit there waiting, because we know at some point you're going to go back to the bottom, and it'll be way faster to do 100 transfer contents than making 100 calls to add sublayer. Yeah? So
I'm assuming shared stage morphing is when you mentioned having placeholders. So I'm assuming it's because you have prims that have similar data or different data in the second, in a different stream. And is that what's happening? Is that why you need, or is it different prims altogether?
It's more about moving up and down the LOP network.
Yeah, okay.
And so we don't care about different prims. We care about active layers. And so, you know, if you just have a cube LOP and a sphere LOP, the cube LOP edits its active layer, the sphere LOP, it's the same active layer, and so we just do a transfer content, you know, one way or the other. If you start doing more complicated things, like you start doing stuff that causes us to introduce more LOP layers, and so you have several LOP authored layers in a row, then as you move up and down the stage, the clearing and the placeholder layers are only for when you don't need that layer anymore on the stage. Like you've moved far enough up the network that active layer isn't on the stage at all anymore. And so in a sense, we really want to remove it, but removing it is expensive, so we just clear it, and that's equivalent, produces an equivalent USD stage. So here is just an example of stage morphing. So top left, you've got node A, and it's added a layer from disk, file1.usd, and then it's added some data into a LOP layer called the sphere1 LOP layer. And then you go to node B, and node B adds another LOP layer, the xform1 LOP layer, adds a couple of USD layers, and then adds another LOP layer. And then you move the display flag back to node A. Nothing needs to cook, so we're just doing stage morphing at this point. And so what we do is we you know, I don't even know whether we start at the top or the bottom, but let's talk about it from the bottom. So we see file1 corresponds to file1. We don't need to do anything there. We see sphere1 corresponds to sphere1. It's the same active layer there. We don't need to do anything. The xform1 LOP isn't on node A's XUSD data, so we clear it, and we end up with a placeholder layer there. File 2 and file 3, we have to remove those sublayers. We can't edit them, we can't clear them, we can't touch them. We have to remove them because they're on disk, and so we're not allowed, LOPS is not allowed to edit them. So we have to actually remove those sublayers, and then the render settings 1 LOP, we can just clear it and end up with a placeholder layer. And then when you go back to node B again, we do the reverse. Placeholder layers become render settings 1 and xform1, and we have to insert those file 2 and file 3. And so you're doing sublayer edits, and that's, you know, can we avoid that? Not always, but if you can, and this is going to depend on your studio, your pipeline, what your LOP network has to do. But if you can get those files 1, 2, and 3 into node A instead, and they're there from the beginning, then, you know, when you go from A to B, you're just adding xform1 and render settings 1. And then when you go back to node A, those just become placeholder layers. And when you go back to node B, they just get filled out again. So it goes from being, you know, adding and removing sublayers to a couple of transfer content calls. Now, obviously, the content is different because you've got files 2 and 3 on the stage in node A, which again is why it has to depend on your pipeline. But if you can do this, this is why certain, you know, switching from A to B is going to be way faster than others switching from A to B.
So every LOP node makes its own sublayer that is different from, like, just for computational, like, proofing purposes, different from, like, where you would have, like, the layers you're making for, like, how you're structuring your USD stage, right?
No, it can. Every LOP layer has an active layer. It can reuse the active layer of the previous LOP node, and by default, that's normally what it does. So if you have simple LOPs like a cube LOP and a sphere LOP, they'll share an active layer. And so the contents of the active layer of the sphere1 LOP is going to contain the cube and the sphere. There are 2 ways you can change that. So a configure layer LOP can say start a new active layer. There's like a little checkbox. And that means that the next LOP is going to start a new active layer. Or you can use the debug flag on the LOP node. And any LOP node with the debug flag is going to start a new active layer. When you go into the USD ROP and you write it out, You know, as long as you haven't explicitly said, I want to save out this active layer to this path, then they are what's called implicit layers, and so they get mushed together, and the USD that gets written out to disk can be exactly the same as if you continue to use the same active layer. Yeah, but yeah, a whole sequence of LOP nodes can reuse the same active layer.
Okay, I'm just curious how, if that does this, how are you able to, when you go back in the network, I can see how like the COOP works from the, you've got a top node, transfer content, it computes, transfer, compute, transfer, compute, transfer. And when you go back up that tree, do you reveal from the top? Or like how do you remove that content? Because you're saying you would clear the sublayer to remove it from the stage?
If you want to remove a sublayer, then you clear it. But if you're reusing the same active layer, so let's say you've got a bunch of nodes in a chain and they're all using the same active layer. So there's only one layer on your stage. When you go from the node at the bottom to the node at the top, it knows that it's the same active layer, right? All the nodes know that the active layer that's on the stage right now is the same active layer that they authored. It might have different contents, but it's the same active layer. And so the node at the top just does a transfer content from its stashed copy off to the side back onto the stage. And then when you go to the bottom, exactly the same thing. It doesn't care what's on the active layer right now. It just knows, well, that's the same active layer, but it's not in my state, so I'm just going to do a transfer content.
Right, and transfer content would be able to remove any prims that were added that shouldn't be there anymore.
Transfer content makes the layers identical, the source and the destination.
Okay.
Cool, I'm almost done. Talk a little bit about the viewport. So the viewport has its own data handle, has its own XUSD data, and has its own stage. It never uses a shared stage. It takes a copy of the XUSD data of the LOP node with the display flag. It does a read lock to get the stage, sends that to Hydra, and that stuff appears in the viewport. Hydra sends it to the renderer and stuff appears in the viewport. When you change one of those LOP nodes, when you change the LOP node with the display flag or you move the display flag, then again, we just refresh that XUSD data. We read lock the viewport, the viewport's XUSD data, which morphs the stage into its new state using exactly the same methods that I described before. So again, trying to avoid adding or removing sublayers, using transfer content as much as possible. And that, it's all about minimizing USD changes, because USD changes cause change events. Change events cause recomposition, and they cause Hydra updates. And so, a lot of what we're doing is just trying to avoid that. I wanted to, yeah, sorry, go ahead.
Is the profile the only way to actually measure performance of your graph?
Yep.
Okay.
A stopwatch, I guess.
Yeah, that's what I've been doing.
Yeah.
Well, I guess I'm trying to see if there's a way to like figure out, intermediate steps where I can be like, okay, is this happening in the right order, or what active layer am I really manipulating, or if it's, actually don't worry about it. We'll have a conversation.
Okay. I just wanted to post these links, and a couple of SideFX links about writing LOP nodes, and some of that stuff I said about the stage is described in that About LOPs document. And then I also want to point to Luca Scheller's USD Survival Guide, which is an awesome website with all kinds of information, more focused, less useless inner details than I've provided here, but possibly more useful hints. So that's it.